Hey there, ladies and gentlemen. So I'm gonna go over a brief presentation here on what molarity is. Um, but I just want to kind of review some of the basics about what a mole is before we get into molarity. Just because if you don't know what a mole is, you can't really move on to the next things because it's all kind of the background items in there. So I have this presentation here. What is a mole? A mole is a way of measuring how much stuff is inside container, and we could have it in terms of atoms, or we could have it in terms of grams. Of course, you should remember Avogadro's number. That 1 mole is 6.022 times 10 to the 23rd particles, or whatever the substance. So in this scenario, I'm just going to use a couple of elements, not the entire periodic table. I'm going to use hydrogen, carbon, and gold. And the question is, what does zero point 0.5 moles of A mean? And A could be anything. So we're going to kind of run through two possible answers. First, you need to recall again that Avogadro's number represents 1 mole of any sample. It doesn't matter whether you're talking about atoms or protons or molecules or shoes. If someone says you have 1 mole of that thing, you have 6.022 times 10 to the 23rd pieces of that thing. It is a gigantic quantity which is not used very often, and therefore the mole is a common substitute for that value. So if you have a half a mole of A, you have a half of 6. A half of 6, of course, is 3. So you have 3 times 10 to the 23rd particles of whatever the substance is. So I'm going to roll through two scenarios. What if A is gold and what if A is methane? Well, if A is gold, then you have 3.011 times 10 to the 23rd gold atoms because there's only one type of particle in a sample of gold, and those are atoms of gold. However, if you have methane, methane is a molecule, formula is CH4. And since its formula is CH4 and these are molecules, if you have a mole or a half a mole of methane, you have 3.01 times 10 to the 23rd methane molecules. Notice that both answers are 3.011 times 10 to the 23rd because you have a half a mole, but the type of particle is varying. You just have gold, so it's atoms. In the other one, you have CH4, which is a shared covalent bonds. That's what we call molecules when they're sharing covalent bonds. And go back and review molecules on your own time. This one's on moles and molarity. Now, that describes the relationship between moles and how many items are inside. What if instead we're talking about how heavy those items are? I don't have to tell you that, if you have the same number of items of two samples, they're probably not going to weigh the same thing. Like, if you have five potato chips and five shoes, those aren't going to weigh the same thing. So chemists have related a nice long list of what a mole weighs on the periodic table. If you go to the periodic table, you'll find the molar mass of any element by itself. And that's what we have in this video here. We have the molar mass of hydrogen, carbon, and gold. And so if you have 1 mole of hydrogen, you have 1.01 grams of hydrogen. If you have 1 mole of carbon, 12.01. If you have 1 mole of gold, 196.97. Now, again, in this example, I said, well, you have half a mole, you have 0.5 moles of A. So what would that be for gold? Well, since 1 mole of gold is 196, a half a mole would be half that. And that's pretty easy. You just divide 196 by 2, and you've got the mass of half of a mole. And that's really easy when you're just dealing with one atom. But if you're dealing with molecules or ionic compounds, you have to pick up all of the atoms and add them together and take into account the subscripts of the formula. And so methane is CH4. So it'd grab carbon, there's only one of those, 12.01, and grab hydrogen, 1.01, but there's 4 hydrogens, so it's 1.01 times 4. We add them together and we have the molar mass of methane. A methane molecule, a mole of methane would be 16.05 grams. 1 mole of methane is 16.05 grams. Again, in this example I generated, you have half a mole. So you take the mass from the periodic table, chop it in half, and you have half a mole, 8.03 grams of methane. Okay, so we've kind of reviewed how to figure out what is in a mole. We could use Avogadro's numbers, 1 mole 6.02 times 10 to the 23rd, or we could use the molar masses from the periodic table, taking into account if it's a molecular ionic compound, those subscripts have to be factored in. Now, what about their look and how they're spread out? Well, so I created two particulate diagrams for these two examples. Here we have a mole of gold, 6 times 10 to the 23rd. I obviously can't make 10 to the 23rd little circles. So what I have here is I have 6 gold atoms, and then on the side I wrote times 10 to the 23rd because it would be a ridiculous quantity. And then I have 6 methane molecules, right? 6 methane molecules, and again times 10 to the 23rd. And I want to point out that both of them have the same number of atoms. They both are 1 mole, but their masses are different. How could their masses be different? In fact, if you look at it, you'd think initially that this drawing here would be heavier. But remember, these masses are really the number of protons in the nucleus, and gold has way more protons and neutrons. I left that out. Gold has way more protons and neutrons in its nucleus, so these are much heavier. In fact, I have an issue with these two drawings. The methane molecule is really light, and it would definitely be floating around in here. These gold atoms would probably not be floating. Oh, can't go through the container. Probably not be floating. They would probably sink to the bottom unless there was something really weird, like they were super duper hot. Gold atoms don't tend to float, at least mine don't. Um, and again, well, what if we had half a mole? With half a mole, we have 3 times 10 to the 23rd. That's half as many atoms. And again, these really shouldn't be floating if they're gold. They should be down on the bottom. And then the methane molecules are so light, they tend to float around and move all over the place, and they're not really stable. There we go, move you. Okay. And half a mole, both have the same number of particles floating around. They both have 3 times 10 to the 23rd. They're both half a mole, and their masses are both half. So there, I've kind of reviewed what the heck a mole is. But let's take it closer in the direction of molarity. So in this example, both of these are methane. They both have 1, 2, 3, 4, 5, 6 times 10 to the 23rd. 1, 2, 3, 4, 5, 6 times 10 to the 23rd. So they're the same number of moles. But the space they're moving around in is very different, right? It's very, very different. And I've labeled the volume this time. I said the volume of this container is 1 liter, and the volume of this container is 0.2 liters. Those are very different volumes. And when we get into molarity, we take into account both the moles, how much is moving around, and the space in which it's moving, the volume. And we measure that volume in liters. And so this is where molarity comes into place. Molarity is both the concentrate is a concentration. It takes into account both the volume and the moles. It's typically written one of two ways. It's either molarity is equal moles divided by liters, or it's written in a simple kind of equation, capital M, meaning molarity, is N over V, moles over volume. Now, one key thing here that I didn't emphasize enough, and for those of you who are actually writing things down at home, molarity is in liters. Molarity is in liters. Okay? It's moles per liter. Um, and so I calculated the molarities of these two methanes up here. We have 1 mole of methane divided by 1 liter. That is 1 molar methane. The concentration of this container is 1 molar. On the other side, we still have 1 mole, but the volume is 0.2 liters. 1 divided by 0.2 is 5 molar. So this is more concentrated. It's 5 times more concentrated. And the whole reason it's more concentrated is that the volume is smaller. These molecules are just closer together. They're more condensed. So molarity tells you about concentration. It's also a ratio of how many moles to how many liters. So we get to the point here where it's time to do some math, and I'm going to run through one example all the way through, and I'd like you all later to pause the video and try something on your own. So we have 4 grams of methane in a 2-liter bottle. What is the molarity inside the bottle? So This is grams, and we're looking for molarities. What should we do first? Should probably change the grams to moles. Yeah, that's a good idea. Let's see if I did that. I did that, yes. I used dimensional analysis. I said 4 grams times 1 mole over 16.05 grams. Where did I get the 16.05? Yes? Yeah, yeah. Some of you probably didn't hear that, but the 16.05 came from the periodic table. Good job, Sally. Bonus points for you. Yeah, we got to go to the periodic table. We got to find the molar mass of our molecule. This was methane again, same methane we've seen already. So now I've got the moles. So I could say, all right, moles. 4 grams of methane is 0.28 moles. And I need to convert that to molarity. So I'm just going to take the moles and divide it by the volume it's occupying, and I have the molarity. There we go. Pretty simple. Um, and this next question, I have a series of weird ideas here. I said, well, sometimes things leak, the particles get out, and then the molarity would slowly drop if the particles were getting out. Now, if the particles are getting out, it's not because the container is getting smaller, it's because some of the particles are being removed. So the volume of the container is not changing, but how much is in the container. So you measure the amount of methane and determine its lost mass. Each day it loses 5% of the methane from the present sorry, 5% of the methane present from the previous day. Determine the molarity of the bottle after 3 days. And you could do this out way far. And later on in the school year, we'll do like natural log graphs and stuff. Ooh, I don't want to scare you. So on day 0, there's 4 grams. We just calculated that was 0.248 moles, and that was 2 liters. And the molarity was 0.125 molar. So it loses 5% each day. So if it loses 5%, how much is left behind? Yeah, yeah. Okay, good job. What is it, Bob? Nice. Okay, Bob. Yeah, so it would be 95% left behind. So I would say, okay, what's 95% of 4? That's how much is there on day 1. What's 95% of that? That's how much is there on day 2. What's 95% of that? That's how much is there on day 3, because it's losing 5% from the previous day. And then I need to convert that to moles and convert those moles into molarity. I'm going to ask you to pause with this screen up here and try to figure out the moles each time and the molarity. Okay, now that you're done being paused, I tried to simulate the pause. You should have something that looks kind of like this. You took 95% would be left, 95% would be left, 95% would be left. And then you figured out how many moles that was, how many moles that was, how many moles that was. And all the container doesn't change, so it's 2 for each. So you did this divided by 2, divided by 2, divided by 2, and those are your molarities. And you can see the molarity is slowly dropping, and you can continue this out, and eventually your bottle's practically empty. That sounds like a fun, complex gas law problem for a different day. But these are the basic calculations for molarity. You need to change masses into moles, divide by the volume, and you've got the molarity. Now, again, the molarity has to be in what units? Yes, Lauren? Liters. Good job, Lauren. Yeah, and if you get those, don't forget. You know what? I'm going to type something in here that I should have said earlier. Wow, that's huge font. Must be important. There we go. Let's just move this over here. There we go. Important because it's gigantic. Totally accidental. But don't forget 1,000 milliliters is 1 liter. So if you have 200 milliliters, that would mean, let's see, 200 milliliters would be 0.2 liters. There we go. Good. Yep, I see that one guy back there who raised his hand earlier, and I completely ignored him on purpose. You know who you are. Um, because your question is about significant figures, as if that really matters right this second. Um, my rule, and generally the College Board's rule, is don't round until you get to the very end. Don't round until you get to the very end, because if you round as you're going, you're going to have this cascading rounding that's going to really add up. So don't round until you get to the very end. Lastly, you're allowed to have extra sig fig in your answer than you have in the given, or one less. You're allowed to have one more or one less. So if you go back to the beginning, I had 4 grams. That's just 2 sig figs, 4.0. So really, these should each only have 2 sig figs. If I have one extra, that's totally okay. 2 extra, that's not good. All right, let's move on. Diluting. When you dilute something, you're not actually changing the number of moles. You're changing the volume that it's in. You're spreading the moles out. So I have this amazing drawing over here where there's 4 moles floating around in the water, and there's still 4 moles when more water is added. And you can see the water is going from 100 to 200, and so it's getting spread out. And I did the calculation. 4 moles divided by zero point 0.1 liters is 40 molar. That number is just huge. It's calculated correctly, but nothing is ever going to be 40 molar. That's ridiculous. But just for calculation's sake, that's a good calculation. Um, and then after it's spread out, we have 4 moles over zero point 0.2 liters. That's now 20 molar. That should make sense. If they double the volume, it's getting spread out, it's half as concentrated. So here we have a question in red. You have 0.35 molar sugar solution, which occupies 100 milliliters. You add 150 milliliters of distilled water, assuming the volume. Assuming the volume. Oh, there's a missing word there. Is additive. Assuming the volumes are additive. What does that mean, are additive? That means you could just add them together. 100 plus 250 is the new volume is 250. So what is the new molarity? Well, there's 2 ways to do this. I'm going to go through one way and then go through the other way. Um, so the first way is you got to figure out how many moles you have. So I have 100 milliliters. I have 0.35 molar. So I have 0.35 molar. I don't know the moles, but I know the volume. And so I solved for the moles. This is how many moles are inside the sugar solution before it gets diluted. So this is how many moles are in this initial solution. Then they add 150 milliliters of water, so our new volume is now 250. The number of moles are the same, just like in this example above, but they're spread out over a larger volume. So what should happen in the molarity? It should decrease. Correct. Good job, man. Lauren is on point. Good job, Lauren. So yeah, the molarity is dropping, and it's always a good idea to kind of ask yourself, does my answer make sense in terms of the problem? I'm adding water, so the molarity should go down, the concentration should go down. That's what I'm seeing. It is going down. Yay me. Uh, Over here, I have in this purple box the dilution equation. This is not an equation that's actually given on the equation sheet in AP Chemistry, but it's a very useful one. Really, all this is they're saying, you know what? If I did the molarity times the volume, I'd have the moles, and the molarity times the volume equals the moles. These 2 pieces up here are actually equal to each other because they both have the same number of moles. And so if I had just plugged in the molarity and the volume and the molarity and the volume and no molarity, here we go. The molarity and the starting volume, then I don't know the new molarity, but I know the new volume. You could solve for the new molarity. Yes. Sarah? It was right? I don't really know you. So Sarah? Okay. Sarah has a question. She notices that my volumes are in milliliters, and I clearly said all volumes must be in liters. Well, Sarah, I'm changing the liters in both sides, and so since both sides have milliliters, I would divide both sides by 1,000. If you divide both sides by 1,000, that actually cancels out of the math. Or if you think about it this way, when I divide the 250 milliliters to the other side, what happens when you do milliliters divided by milliliters? Yes, they cancel. Good job. Yeah, milliliters divided by milliliters should cancel out. So the only unit left would be molarity, which is always per liter. So in this case, since you have the unit on both sides is the same unit, they would cancel out. If for some reason they weren't the same unit, let's say someone evil gave you liters and milliliters on the other side, you'd have to sync them up before you did the division. All right, let's see what else I've got planned. Molarity and stoichiometry. Everyone loved stoichiometry. I saw kids in the hallways talking about it. They were just so excited. They're like, oh, stoichiometry. Now, honestly, a lot of you all probably did like stoichiometry because it was just simple ratios and applying math ratios. And that's all we're going to do here with this molarity stuff, is we're going to kind of sync that together with what we've already been doing. So we have 100 milliliters of 1 molar silver nitrate. That's this silver nitrate is this guy right here, in a beaker. In a second beaker, we have 120 milliliters of 2.2 molar sodium carbonate. That stuff here, sodium carbonate. You mix the solutions together, and the new volume is 220 milliliters. Looks like it was perfectly additive. Below is the reaction that occurs between them. Determine the mass of the solid silver carbonate created. Now, I made the solid part blue here to make a pop for you. I didn't have to do that, but I decided to. Stoichiometry is usually done with moles or sometimes starts with grams. So the first thing I would have done is this. I would have taken those molarities and volumes and calculated the moles. So I did molarity times volume, and I got 0.1 moles. And then I did the molarity and the volume, and I got 0.264 moles. And I want to point out in this stoichiometry question that we have two givens. We have a given about the silver nitrate, we have a given information about the sodium carbonate, and we're asked for this right here. This is the question right here. The question is X, right? How many grams of this? That's the question. So we've got to use this information, and it ends up being a two stoichiometry problem question. So bam, there's the first stoichiometry question. We take the moles, and this is the mole ratio. It's the ratio between silver nitrate, two silver nitrates produce one silver carbonate. Two silver nitrates, one silver carbonate. Why did the silver nitrate go on the bottom? Great question, Frank. Well, you have silver nitrate to start with. We need units to cancel out and formulas to cancel out. So this is moles of silver nitrate, so I need those to be on the bottom. And the moles of what I'm looking for is on the top. That ratio cancels out, and I could make 0.050 moles of silver carbonate. All right? That's based off of one given. Based off of the other given, I'm going to do the same thing. I'm going to use that 0.264. It's a 1-to-1 ratio, so guess how much you can make? It's 0.264, 1-to-1 ratio, 0.264. So before I go to the next blue block, I want to remind you of a stoichiometry concept you may have forgotten, and that's that oftentimes a reactant limits how far a reaction can go. It limits what can be produced. And we called that one the limiting reactant. So based off of these two answers, 0.264 and 0.050, it looks like the silver nitrate is limiting how much silver carbonate could be produced, whereas the sodium carbonate could make more silver carbonate. If it runs out of silver, it can't make any more. Once it's out of silver, the reaction is going to stop. And so I'm going to use this 0.050 moles of silver carbonate to finish the calculation out, and that's what I'm going to base my mass on. And now that all of the math is, 1 mole of silver carbonate is 273.93 grams of silver carbonate. Let's ask Lauren where I got the 273.93. Lauren? Yeah, exactly, Lauren. I went to the periodic table. 2 silvers, a carbon, 3 oxygens, smashed together. That's the molar mass of silver carbonate. And I used that to calculate the product. So now that I'm done with all of the math for this question, now I am going to round. I had, go back to the very beginning, I had 100 milliliters and 1 molar, that's 2 sig figs. So I'm going to take this and just go back to 2 sig figs. So they should make about 14 grams of silver carbonate, maybe 13.9, maybe 14.1, but really about 14 grams of silver carbonate based off of these molarities. I'm not going to get into sig figs right now, that's a different question. There is a follow-up question below all of this stoichiometry. What is the molarity of each ion that is still dissolved in the solution? So when the reaction's over and all that silver carbonate is turned to a solid and fallen to the bottom, some ions are still dissolved in the water. It's only the silver and the carbonate that are a solid. So the sodium and the nitrate, they're aqueous. They're dissolved in water, right? The silver and the carbonate is in the solid. It is possible that unless it was exactly equal, silver or carbonate might still have some remaining in the water. And the way we're going to do that is we're going to use the whole limiting and excess reactant concept. So was the silver or the carbonate limiting? Yeah, the silver. The silver was the limiting reactant. So let's kind of scroll down here. Silver is in the limiting reactant when making the silver carbonate, so there should be no silver still floating in the solution. The nitrate, the nitrate is easy to work with. It starts dissolved and it finishes dissolved. It's aqueous the entire time. Its molarity does change because there's more volume afterwards. So the zero point 0.1 moles of nitrate is now spread out, so it's a little bit diluted down. It's been diluted, but it hasn't reacted. The sodium is a little bit harder because this 0.264 is for the whole compound. If you look at that compound, how many sodiums are in that compound? Yes, Sally, there are 2 sodiums. So this is the moles of compound, and it gives off 2 sodiums. So I took that value and I doubled it because there's actually 2 times that value of sodium in there, and then I divided it by the volume. Now the carbonate is the tricky one because the carbonate was in excess. So some of the carbonate is in the solid and some of the carbonate is still floating around. It's in 2 spots. So this is the one we have to be careful with. So first of all, and that's what I drew. The hardest one to solve. Some of the ions are in the solid, some are still dissolved. We started with zero point 0.1 moles in the solution. So zero point 0.1 moles were floating around. And then we made 0.05 moles of the carbonate, which means that of the 0.1, 0.05 got removed from the solution, right? There was 0.01 that was aqueous. Now there's 0.05 that is solid. So that means there's still 0.05 moles that are floating around in the solution. And that doesn't answer the question because it says, what is the concentration? What is the molarity? So the molarity of the remaining carbonate, this is the 0.05 that's in the solution divided by the volume of the solution. That's the molarity of the remaining carbonate. That's by far the hardest question here, this C. And you might need to go back and rewind this video and watch that again. Okay, so in conclusion, what the heck a molarity? Molarity is a measure of concentration. It shows the relationship or ratio between moles and volume. And I actually put 2 different containers here that both have the same molarity. They're both 25 molar, which again is an insane number. They're usually like 0.25, but I decided to keep the math a little bit simple here. Um, Actually, I just realized something. This should be 200 and that should be 400. Otherwise, my math is false. And I know how much that bothers some of you when my math is wrong. Let me just, there we go. Okay. So I have 5 moles, 1, 2, 3, 4, 5 moles floating around in the solution divided by the volume of the solution is 25. Over here, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 moles divided by double the solution. So this is double the moles and double the solution. So it's same molarity. And so the relationship of molarity just shows you the ratio between the two. It doesn't tell you how much is really in there. It just tells you the relationship between the two. I found 2 websites where you could go practice some of these things. Where if you select an answer and hit submit, it tells you if you're right or wrong. and I thought you might enjoy / appreciate being able to do a little bit of practice. So pause and write those down, and have a good day. All right.